Hi all, you should have the sheet out in front of you. We're going to talk through some linear programming. And then from there, we're going to do a couple of examples. This is the introduction to this. We're going to spend about 3 days going over this and then a couple of days cleaning things up. So on the back side of your sheet, I've got, you can write down the objective, which is to write inequalities, to model constraints of a situation and find the vertices of the feasible region, otherwise known as a very big system of inequalities. Obviously pause when you need to. And then for linear programming, that is known as a process of optimizing a linear function. What we're going to do is we're going to have a function that we're going to plug all of this stuff into at the very end. What we want to do is look for the best points to try this out. And what linear programming will do is it will allow us to find those best points. Okay. And the constraints, if you think about what the definition of constraint means, share it with somebody. From there, constraints are the system of linear inequalities for a linear programming problem, which is very redundant. Basically, the graphs of the linear inequalities are the constraints that form the feasible region. Okay, feasible region is possible solutions. So again, what we're going to try to do is that the first couple are going to be very, very basic, just so that the numbers are nice. You don't have to worry about graphing it. We can deal with the points relatively easily, and then starting tomorrow, we're going to get into some more realistic, real-life applications. But this is just some basics. All right. So here's an example. School board is investigating various ways to compose a faculty of a new elementary school. So they can hire teachers and program assistants. And from there, they give you 4 constraints. The constraints are going to be the building can teach and hold no more than 70 faculty members. There's a minimum of 30 faculty members total. There must be at least 10 teachers, and the number of program assistants must be at least half of the numbers of teachers. So as always, define your 2 variables. What are the 2 things that we don't know exact numbers of? Good. We have teachers. And we have program assistants, otherwise sometimes known as teaching assistants. Now, from those 4 bulleted items, now we're not always going to give you guys bulleted lists to pull equations off of. We're doing that because these are the basics. Eventually, what we're going to end up doing is just giving you a situation, and you have to pull off how many there are. So if you think there's 5, you write 5. If there's 4, if you think there's 4, you write 4. So from there, constraints. So go ahead and take a second. I want you guys to write down the 4 constraints. So for example, the first one, you would say, okay, the building can hold no more than 70 faculty members. So that's the faculty members, X plus Y. And it can hold up to, but not more than 70. So pause it, take a second, write down what the equation should be. Inequality should be. Here are your other 3 that you and your friends should have come up with. Must be at least 10 teachers, so X has to be bigger than or equal to 10. This last one is usually the one that sometimes will throw people. If you're not sure, it says number of teachers have to be, or number of program assistants have to be at least half the number of teachers. Oftentimes, the 1/2 gets put on the wrong side. If you're not sure, do something like this. You've got PAs, and you've got teachers. So if the number of teachers is 100, how many PAs would you need? 50. If you have 60 teachers, you would need 30. So how would I do that? Oh, I'm multiplying this by 1/2 if I want to make them equal. So once again, if you're not sure, make a simpler problem, plug in some stuff so you can see what the patterns are, and then apply it to what you're doing. So those are going to be the 4 inequalities that we're going to graph. Whoops. I have no idea how I skipped a page. Sorry. All right, so these are going to be the 4 constraints that we're moving. And we're going to graph these things down here. Now, first thing you have to ask yourself is, why did Mr. Hayes not label his axes? The reason why Mr. Hayes did not label his axes is because that's your job. I'm trying to turn you into responsible young adults. And also, apparently, moving graphs around willy-nilly. All right, let's move these down here. So we can see the graph nicer. All right, so label our axes, X and Y. We've got number of teachers down here. Now the question is what we're going to use for our scale. What is the largest value that you can get out of this? So you're going to look at your 4 restraints, and you're going to say, well, X is greater than 10, that's doable. So I have to go by at least 10s. On the other two, X plus Y is less than or equal to 70 and 30. If X is 0, Y is going to have a value of 70. So that would put me up to 70s. So if I count by 10s, when you do this, please make sure you skip the first one and start with 20 there. Don't. Sloppy work just leads to sloppy people. All right, so then from here you're going to graph these points. Now there's a bunch of different ways, or graph these inequalities. There's a bunch of different ways you can do it. I'm going to put a little work area up here, over on the side. So for X plus Y is equal to 70, oops, is less than or equal to 70. One of the ways you could do it is you could treat it like it's solve for Y, find Y-intercept and your slope. Only issue that I have with that is that your slope will work only if your two axes have the same if your 2 axes have the same scale. So if we were counting by 20s on one and 10s on the other, up 2 and over 1, up 2 and over 1 wouldn't work. Okay, so be careful of that. So anyway, for this one, oftentimes if you find your y-intercepts and x-intercepts, you can be in good shape. So if x is equal to 0, that implies that y has to equal 70. So one of your points is going to be here. And likewise, if y is equal to 0, that's going to give me x is equal to 70. So one of your boundaries here is going to be running between those 2 points. So take out your straight edge. You're going to draw a nice line. Now, we're going to, oops, sorry, stepped on my cord. Hopefully you didn't see that. So, next question, we're going to shade above or below. Since we're talking about numbers that are less than that, like if I plugged in 0, 0, the origin, that'd be a true statement. And so I'm not going to shade in really heavy because we've got a lot of graphing to do and we don't want to overlap too much. But it's something to keep in mind. So now what we're going to do is we're going to do the same thing. Oh, by the way, here, let's do this. I'm going to change this to blue so we can match the equations with the graphs. So now we're going to do the same thing with the next equation, or next inequality, excuse me. Apparently I erased it. Not good. So x plus y has to be at least 30. So it's going to actually be something similar. X equals 0 gives me y equals 30. If y equals 30 or 0, that's going to give me an x-intercept of 30 as well. Now, the only difference here, however, is that you're going to be bigger than that. So when you graph this, we're going to be shading on the other side from the origin. And that should be a solid line, as you know. I'm sure some of you are yelling at me already. And then we're going to shade above that. You know what? I forgot to get my crayons out. Let's do that. Red crayons. All right. So I'm going to shade on this side here. So right now, if it was just up to these 2 inequalities, anything in that shaded region where it's both blue and red would be potential numbers of teachers and program assistants you could hire. Okay. Now for the last 2, these are probably some more of the easier ones, so I'm not going to have an area here to work. And apparently I erased the other one too. We said what? X has to be bigger than 10, right? So, bigger than or equal to 10. We're going to make this one green. Maybe. So if x is bigger than 10, you've got another line that's just going to be a vertical line at 10. So it's going to be here. So now we've got a different, the feasible region that we have now. Technically, we could go through, I could ask you and tell you feasible regions are also bigger than 0, and both, you had to hire at least one teacher, or, something like that. We're saying, well, you have to have at least one program assistant or something like that. Generally, we try to think that you're probably smart enough to know that you can't hire negative program assistants. So now we're going to shade above this, or to the right of this, because we want values that are bigger than this. So that's going to be, now I could shade up here too, that's perfectly fine. I'm generally just sticking in what the feasible region should be, is y erased all the crayons. Now the last one, y equals 1/2 x. Again, as I said, you could use a slope. That only works if your axes are the same. So another thing that you may want to do is just kind of plug in points. So I'm going to make this one black, since it's the only other real crayon color I've got easily accessible to. So 0, 0 is going to work. So if I plug in x equals 0, I get 0. So then ask yourself, okay, well, if I had 40 teachers, how many program assistants must I hire? Oh, that's going to be 20. And then you got your 2 points, and away you go. Now again, remember, this has to be at least this, so we're going to shade above this value. So when we shade, you're going to be somewhere in here. So this area right here is your feasible region. Anything here in black is going to be an acceptable number of program assistants and teachers that would fit the school board's criteria. So what we've done now is, instead of having to figure out, does this work, does this work, does this work, we can just look and say, hey, is that in the graph, and we're good. Now, as we talked about, and you don't have this in your notes, we're going to add it to it in a second. You're going to look through and you're going to ask for the vertices of that feasible region. Oh, by the way, here, just make points. This is that right there. Feasible region. Those things are feasible. If something's feasible, that means it could work. Now you're going to find the vertices. So your vertices are right here. So one of them is going to be at 1060. Another one of them is going to be here at 2060. So we have 10 teachers and 60 program assistants, 20 teachers and 60 program assistants. We have another one here at 20 teachers and 10 program assistants. And we have one over here that's not at a nice, neat coordinates. So what sometimes you're going to have to do is you're going to have to do a system of equations where you actually, to use the inequalities. Sorry, this should be greater than or equal to. You're going to use the system of inequalities to solve for that point. So in this case, we need the system, the black line is y. We're going to use y is equal to 1/2 x because that's what the line is. The other one line that's intersecting is going to be the one where it is x plus y is equal to 70. And then you're going to solve that. Substitution would be beautiful. Remember, no decimals, because decimals are sloppy, especially in times like this. Now, do not be the person who says, oh, well, then x is 210 divided by 2, so it's 105. No. Remember, multiply by the reciprocal. And that's not opposite, it's just the reciprocal. You flip it. So now I'm going to come up with x is equal to, so that's 140 over 3. So that's going to be 6 2/3. Now, don't round it. Don't give me this 46.7 stuff. Oh, it's just 47, because we're going to talk about that in a second. Rounding is not always your option. So the other number, when you plug it in, we're going to 23 1/3. Now, what is the problem with that? Well, you can't have 1/3 of a teacher. I mean, 1/3 of a program assistant, nor 2/3 of a teacher. So anyway, so what's going to end up happening is that I can't round up, because if I round up to 47 teachers, then you're no longer in the feasible region. So we need to treat this as 46 and 23. So you're going to round down. So that's going to be your other feasible region. All right? vertices, sorry. All right, now, what you're going to end up doing, this isn't on your notes, but who cares if I have the vertices, right? Well, this is the whole reason why you do it. Anything in the feasible region is a possible solution. Your vertices are either places where you generally will be places where you maximize or minimize your opportunities. So let's say the school board says, okay, so if an average teacher's salary is $50,000 and an average PA's salary is $25,000, what's the maximum and minimum salary costs? So the first thing you need to do is you're going to need to come up with a formula that will work for this. So how much is it going to cost total salaries? And the way that you can do that, obviously, is right from here. So you've got X is teachers, so that means you got $50,000 per teacher. So cost equals plus $25,000 per PA, and that's it. But what you're going to do here then is you're going to take your 4 vertice points up here, the 10, 60, 20, 60, 20, 10, and 46, 23, and you're going to stick that in there, stick those into your cost equations. Because again, remember, those are points of opportunity. Those are generally going to be maximums and minimums of what you can come up with. So right now in your groups, or on your own, pause this, and then everybody take one. If you have only 3 in a group or something, fight for it and see who gets to do the second one. And then when we come back, we'll double check and talk it through. All right, so we've got, let's see, for 1060, so 10 teachers and 60 PAs. That would cost you, what, 500,000, 150,000. That would cost you $2 million. If I had 20 teachers and 60 PAs, that would cost you, what, an additional 500,000, so $2.5 million. If you had 20 teachers and 10 PAs, that would get you, what, 1.25? And last but not least, the 46 and 23 is going to give you a very, very large number. And that's going to be $2,875,000. So if you really just wanted to worry about costs, you'd go 20 teachers, 10 PAs. Now, obviously, there's other things you have to worry about. Student enrollment. What's the minimum number of student-teacher ratio that you want? Things like that. So this isn't necessarily the end-all be-all, but this does give you some points in which to start having conversations about what do we want to do, how can we save money, how can this work, can this be more effective, et cetera, et cetera. Okay? Now, on the second sheet that you have is your homework, and what I want you to do is this. So I want you to take a second. We're going to pause this, and I want you to write out your 3 constraints for this. And then after you get done with that, we'll pause it again, give another 5 or 10 minutes, and then show me what the feasible region looks like. Okay? So your constraint should look like this. So X is the number of medium pizzas. So X must produce at most 600. So you can't go bigger than that. And you must make at least 700 pizzas a week. So that means this can be bigger than, greater than, or less than, or equal to. And the number of large pizzas produced cannot be more than 2/3 of the medium. Now take a shot, double check your work, and graph that. So pause it for a second and come on back and check your graphs. So counting by 100s, 200, 400, 600, 800. I know I can read my own writing. That's impressive, isn't it? And of course, you already have your labels labels on your axes. So this is going to be large pizzas. If I haven't told you already, I make some of the best pizza you will ever have. Stuffed, deep dish, thin crust, does not matter. Anyway, so you're going to graph those out. So you need to be x is less than 600. So we're going to make that one, let's do that one in black. So you've got a nice vertical line there. At the blue one, which is x plus y is equals 700, I think you guys probably... Now again, this only works because x and y is the same, have the same coefficients, but there. We'll thin that up a notch, maybe. Or not. All right, so first of all, the first one, by the way, we're going to shade less than this. So we're going to shade on this side here. We need to be bigger than the 700, so we're going to be shading on this side here. And we need to be less than 2/3 x. So again, pick some numbers that work. And let's do this one in green. So if x is 300, y is going to be 200. If x is 600, then this is going to be 400. Okay, and then you can draw there, another line. Remember, life is better with sound effects. We need to be less than that, okay, which means that we're going to be going down this side. So we need to be bigger than the black, left of the black, bigger than the blue, less than the green. So that means that your feasible region is actually very, very small if you want to make this work. And in fact, it's going to be this area right here. So the vertices that you can go off here and do. Okay, so the important vertical points here are going to be this one here. So you've got 600, excuse me, you have 600, 400. You also have 600 and 100. And the last one over here should be, if I drew the points better. So you know, you're going to have to figure that one out on your own, aren't you? So you're going to have to figure out the vertical vertice that's going to be between y equals 2/3 x and the one where it's x plus y is equal to 600 or 700. So those are the two lines that are there. Oops, I got turned into a highlighter. So if you solve this system here, then you can figure out what this vertex is right there. Okay? So finish this up. We'll finish out the other one tomorrow. We'll talk through it, and then we'll show you guys how you can actually... There is no, obviously, optimization point to this one for this one. It's just a matter of setting it up. Tomorrow, we'll talk about upping this, making it a little bit more involved, a little bit more complicated. But again, just for the basics ones, graph your lines, look for the intersections, and away you go. We'll talk to you soon.